All right, so Newton's first law talked about everything remains in its state of motion unless acted upon by an unbalanced external net force. Newton's second law is going to say, well, what happens when you do have that unbalanced external net force? So we have a couple variables involved. If you look, for example, at anything that's moving, how does acceleration of the object depend on that force? And can we represent this in an equation? Because it's going to be acceleration. Remember, inertia says you don't change your motion unless you have a net force, non-zero net force. So if we have a non-zero net force, we're going to have a change in motion. So it's going to have some sort of relationship with acceleration. Okay, and it turns out that that relationship is directly proportional. This is not an equal sign, by the way. That just means proportional to. So what is it? What does that mean, proportional to? It means if I double the net force, I double the acceleration. If I triple the net force, I triple the acceleration. So it just means if F net increases, A increases. If F net decreases, A increases. So the more force you put on something, the greater its acceleration. And I think that sort of makes sense, right? If you go to push something, it's going to accelerate. It's not going to slow down. Unless, of course, you're pushing something that's moving towards you. Right? It's also inversely proportional to mass. So what does that mean? It means if mass increases, acceleration decreases. So you can imagine trying to push this sled with one light object on it, and then trying to push this sled with the exact same force filled with all sorts of heavy boxes. Right? Our second example will have a much smaller acceleration. So in a sense, that makes sense as well. And we can put these two ideas to say Newton's law. Now, written with words, Newton's laws looks kind of long and confusing. It says if the net external force on an object is not zero, the object will accelerate in the direction of the net force, and the magnitude of that acceleration is directly proportional to the net force and inversely proportional to the mass. I have no one ever repeat this to me when I say, what's Newton's second law? Everybody says this. F net equals ma. It is the equation in classical physics. If you never do physics again in your entire life, I guarantee you 50 years from now, you will still remember F equals ma. Right? I would say probably it's one of the next most famous equations other than E equals mc squared. That's an equation everybody has probably heard of, even though in this class you might not know what it means yet. But E equals mc squared is a famous equation. This one, not everyone has heard of it, but if you've ever taken any physics class, you know F net equals m. All right, so how are we going to actually use this to solve a problem? Well, you can go one way or the other. First, just like we've learned, we're going to draw a free body diagram. That's the first thing we learned when we started this unit. Then we learned how to calculate net force. And you add up all the forces that are on your free body diagram. Once you have net force, you can use Newton's second law to figure out acceleration. And once you know acceleration, we can go back into the first unit where we had acceleration equals change in velocity over time. And you can figure out anything you need to know about its motion, its position, its speed, right? You can also do it in reverse, right? It depends what information you have, right? If I give you all of this information, you can use your motion equations to calculate acceleration. Knowing that, you can work backwards, calculate net force, and then figure out what its free body diagram might look like. But in this course, pretty much most of the time, we're going to be going down this chart. So we're going to be starting with free body diagrams. Right, so let's look at some example problems. Here's the first one. A worker applies a force of 360 newtons east on a trunk of mass 50 kilograms. A friction force of 300 newtons acts in the opposite direction. Okay. Now, in this question, I've actually told you first to draw a free body diagram and then find the acceleration. However, I may just tell you find the acceleration. You have to remember that the first step is to draw a free body diagram. And anytime I give you a forces question, you should first draw a free body diagram. So let's draw a free body diagram. Okay, so we have an applied force of 360 newtons east. Okay, and our mass is 50 kilograms. That we'll just remember, that's M. And a friction force of 340 newtons, and that would be in the opposite direction. 340 newtons opposite of east would be west. Okay, now you will have gravity, of course, and you will have the normal force. But since this is just an object on a horizontal surface and it's being pushed horizontally, these two forces are going to be balanced. They're going to be equal and opposite, and because they're perpendicular to acceleration, they're not going to affect our acceleration at all. Okay, remember we can consider our vertical motion and forces completely separate than our horizontal ones. So in this question, all we care about are those horizontal ones. So when we find net force, which is the next step in our chart that I showed you, the net force, we're just going to look for the net force in our horizontal, which we called x from a Cartesian coordinate system. Let me make this a little bigger here. Alright, so we're going to add these two forces together then. We have 360 newtons east plus 340 newtons west. Alright, but I can't just simply add them because their directions are different. So I need to change those two things there. I'm going to change positive to negative and west to east. So that would be 360 newtons minus 340, which gives me 20 east. Alright, so we did our first step, which was drawing a free body diagram. We did our second step, which was finding net force. Our third step is going to be finding acceleration. And to find acceleration, we need to apply Newton's second law, where F net equals mass times acceleration. Now, a lot of the times you're not going to use it like this. You're probably going to divide both sides by mass first. So you divide both sides by mass. Mass cancels on this side. Right? And just move over here. You'll get acceleration equal to F net divided by mass, which in our case is 20 newtons east divided by the mass, which was 50 kilograms. You get units of newtons per kilogram, and those units are equivalent to meters per second squared. So we end up with 0.4 meters per second squared east. Okay, so there's our acceleration. All right, in this question, we're giving a little bit different information. So we have the mass of the wagon, but then we're given acceleration. So we don't need to find acceleration. We're being given acceleration. Then it says the frictional force total 50 newtons. So let's still draw our free body diagram. Here's our free body diagram. Now we have a frictional force. Let's just put it in this direction of 50 newtons. And then a boy pushing it horizontally. Of course, it would be in the opposite direction of friction, with some unknown applied force. And that applied force is causing this acceleration. All right, so now we're going to work backwards. Okay, I can't solve for net force because I don't know what the applied force is. But I already have acceleration. So let's jump over to Newton's second law, which says F net equals ma. I have mass and I have acceleration. So I can figure out what F net is. It's just our mass, which is 10 kilograms, times our acceleration, which is 2.5 meters per second squared. Okay, let's just write forward, because it doesn't specify. So that's going to give us, well, 10 times 2.5 is 25 newtons forward. So that's our net force. And what's net force again? Net force means that if we add these two forces together, we get 25 newtons forward. So let's do that. So our net force is going to be 50 newtons. Let's just call this backwards, and this will be forwards. So 50 newtons backwards, plus some applied force, which we don't know. Sorry, you can't see that. All right. Now the net force I do know. I just calculated that. It's 25 newtons forward. And that's going to equal 50 newtons backwards plus Fa. All right, so now I need to solve for Fa. So I can bring this term over to the other side by subtracting it from both sides. So I get 25 newtons forward minus 50 newtons backwards equals Fa. But this is forward and this is backwards, so I need to change this to forwards. In order to do that, I need to take the opposite sign. So this is going to become positive. 25 plus 50 gives us 75 newtons forward equals Fa. And if we look at that, look at our free body diagram. If this is 75 and this is 50, the difference is 25, which is our net force. And that net force is what caused that acceleration. So this example again is giving us a bit different information. So it says, in an extreme test of its braking system, under ideal road conditions, a sports car initially traveling at 28 meters per second south. So initially traveling, and that meters per second is a velocity. So it's telling us initial velocity, 28 meters per second south. This seems like the previous unit, but remember, force causes motion, so the two units are sort of intertwined there. Applies its brakes and comes to a stop in 3.5 seconds. So we have time is 3.5 seconds, and they're also telling us something else. They say comes to a stop. So that means our final velocity is 0. It says the mass of the car is 1.2 times 10. That should be to the power of 3, not times 103. So times 10 to the power of 3. Calculate the car's acceleration, and then 2, the net force. So when we're trying to calculate acceleration, we can just use our equation for acceleration that we learned in the previous unit. A equals VF minus VI over time. Because we have everything here, except VF is 0. So we get 0 minus VI, so minus 28 meters per second south, right, divided by our time, which is 3.5 seconds. So that gives us our acceleration of minus 8 meters per second squared south. But minus south is the same as positive north, so 8 meters per second squared north. That's the first part, our acceleration. The second part asks for net force. So that's when we can go and use Newton's second law. F net equals ma. I always forget my vector signs. Then we know mass and we know acceleration. So mass is 1.2 times 10 to the power of 3 kilograms multiplied by 8 meters per second squared north. And then we get net force, which would be 9,600 newtons. And again, net force has a direction north. And we can also continue to write that in scientific notation just to express the correct significant digits.